All right, this new chapter that we're working on is on infinite series, and before we can define what a series is, we need to start with sequences. So a sequence is really a function whose domain is the set of positive integers. Think of it as just a list of numbers separated by commas, right? Just like a list of what those values are. A lot of the time, we might start with our first entry being called like A1. Sometimes it's convenient to start with 0 as the first entry, so you might see a sequence starting at A0, A1, A2, and so on. Usually when that happens, it'll be pretty explicit. Most of the time, we start with A1. So in example 5.1, it says list the first 4 terms of this sequence, and this sequence is defined by a sub n is given by 3 plus -1 to the n power. So we're just going to find these different values. A1 is 3 plus -1 to the 1 to the first power. So that's 3 minus 1, or 2. A2 is 3 plus -1 squared, so that's 3 plus 1, or 4. A3, so that'd be 3 minus 1 again, that's 2, and A4, and that's 3 plus 1 again, or 4. I think we can sort of see what's happening, right? That -1 to the n power is either going to be a -1 or a +1, depending on whether n is even or odd. Here's another sequence. Our bn's here are defined by n squared over 2 to the n minus 1. We're going to find the first 4 terms. So b1 is 1 squared over 2 to the 1 minus 1, which is 1 over 1. That's just 1. B2 is 2 squared over 2 squared minus 1. So that is 4 over 3, 4/3. B3 is 3 squared over 2 cubed minus 1. That is 9 over 8 minus 1 is 7. And B4 is 4 squared over 2 to the 4th minus 1. So that's 16 over 15. What we're going to be concerned with primarily in this section is whether or not a sequence converges to a particular value. So we define the limit of a sequence. When we talk about the limit of a sequence, we are very specifically talking about the limit as n approaches infinity of those terms. So as n grows, as you go further out into the sequence, are those values approaching a single value? And we have this sort of this epsilon definition that just says, look, for every, we say that a sequence converges if for every epsilon greater than 0, there exists some number, big M, such that an minus L is less than epsilon whenever n is greater than m. What that means is that we say that the limit of a sequence is some value L if, now when they say for each epsilon greater than 0, what we're thinking of is that epsilon could be very small. Like think of an epsilon that's bigger than 0, but like very small, like 1/1000th or 1/1,000,000th, all right? And think about forming this epsilon band around this value L. And it says that there exists some big M greater than 0 such that absolute value an minus L is less than epsilon. That means that the distance between the terms and that limit L will be less than epsilon whenever n is bigger than m. That means that when we go out far enough into the sequence, and in this figure it looks like maybe that's happening right here, right? That these terms in the sequence sort of enter this epsilon band and they never leave. And you can do that no matter how small you make epsilon. So it just means that the terms of the sequence get closer and closer and closer to that limit L. In example 5.3, we're going to find a limit. It says find the limit of the sequence whose nth term is given by a sub n is 1 plus 1 over n, all raised to the n power. Now, I guess it looks like maybe they're suggesting that this sequence does in fact converge. Some sequences don't. Not every sequence converges. So notice that we have n appearing in both the base and the exponent. And it might not surprise you in that case that we're going to start by saying let's let y equal this limit as n approaches infinity of 1 plus 1 over n to the n power. So we want to find the value of y, and what we're going to do first is take the ln of both sides. So ln y is the limit as n approaches infinity of ln of 1 plus 1 over n to the n power. The whole purpose in taking the ln of both sides is that I can use the properties of logs. So I'm going to grab that n exponent and bring it down as a factor in front. So we want to evaluate this limit. Now, remember what we did at the end of the last chapter? One of the things is how we evaluate these limits. Notice if I let n grow without bound, here n, of course, this factor of n approaches infinity. Here, if n grows without bound, 1 plus 1 over n approaches 1, and ln of 1 is 0. So this is an indeterminate form. We can rewrite this as ln of 1 plus 1 over n divided by 1 over n. So instead of multiplying by n, we'll divide by 1 over n. We do that because now this is the form 0 over 0. Now, technically, because a sequence is a function whose domain is the positive integers, we don't really think of this as a continuous function for which we could take the derivative. However, as n grows without bound, I mean, the limit of this sequence of discrete values will be the same as the limit of the continuous function. So what we're going to do, and I'm actually going to kind of write it out this way, although a lot of times people might skip this step, is I'm going to say this is the same as the limit as x approaches infinity of ln of 1 plus 1 over x divided by 1 over x. Oops, 1 over x. Where these are continuous functions. I'm not saying that the sequence of discrete values is the same as the continuous function, but I am saying that their limits are equal. So, and what's important about this is that now, since it's in the 0 over 0 form, and these are continuous functions, I can apply L'Hopital's rule. And at this point, you know, this example might look a little familiar. We've actually worked out this limit in the past. So this is the limit as x approaches infinity. I'm going to apply L'Hopital, take the derivative on both the top and the bottom. So this is 1 over 1 plus 1 over x times negative 1 over x squared. And then on the bottom, the derivative of 1 over x is negative 1 over x squared. We can cancel this common factor. Now, as x approaches infinity, 1 over x approaches 0, so this whole limit is equal to 1. And so what we found is that ln of y is equal to 1. And that means that y is equal to e to the first, or e, and that's the limit that we want. This is the limit as n approaches infinity, 1 plus 1 over n to the nth power. So before we evaluate some more limits, we're going to go over some properties of limits. the first property, so let's say we have a couple of sequences, right? And we have the ANs are approaching L and the BNs are approaching some value K. The first property says that we can split up a limit over a sum or a difference. So if I could say, oh, these terms are approaching some value L and these terms are approaching some value K, I just evaluate them separately and add them together. I can also pull out a constant factor as long as C is any real number like a constant, right? So there's no n's in that. You can also split up a limit over a product, right? So I can just look at what each factor is approaching and then just multiply those together. And you can split up a limit over division as long as the BNs are not approaching 0 and the BN terms are not 0. So let's evaluate some limits. Let's determine whether or not these sequences converge. And just like we saw when we were evaluating limits, when we were looking at improper integrals, you know, we say a sequence converges if it converges to a single value, and we saw that in that definition. If it does anything else other than converge to a single value, then that sequence diverges. So we'll note here that we already looked at terms of this sequence, that -1 to the n term. This alternates between -1 and 1. And that means that the terms an alternate between 2 and 4. So the terms are not approaching a single value. They're not blowing up either, but they're not approaching a single value, and that means that this sequence of a sub n values diverges. All right, this next one, our BNs are defined by n divided by 1 minus 2n. So to see if this converges, maybe let's just look at the limit. Can we evaluate this limit as n approaches infinity of n over 1 minus 2n? Now, if we let n grow without bound, both the top and the bottom grow to infinity. You could apply L'Hopital, although that might be a little bit like hunting a mouse with an elephant gun here, because we do have an algebraic tool. We can just multiply top and bottom by 1 over n. And we've got 1 over n minus 2, and we do that distributing. And now as n goes to infinity, this 1 over n goes to 0, so we get 1 over -2 or -1/2. So these terms get closer and closer to 1/2, and we would say that this sequence converges to -1/2. And we have some notation that can indicate that. If a sequence is converging to a value, we use the single, not an implies arrow, but just the single arrow to the number. In example 5.5, we're going to show that the sequence whose nth term is given by n squared over 2 to the n plus 1 converges. So let's set up this limit. Limit as n approaches infinity of n squared over 2 to the n plus 1. Now, if n grows without bound, the top blows up, goes to infinity, the bottom goes to infinity. But this time we don't quite have a nice algebraic tool like we did before, because we have the exponential term in the bottom. So this would be a great time to use L'Hopital. So again, I'm just going to rewrite this and say that limit as n approaches infinity of that discrete sequence is equal to the limit as x approaches infinity of this continuous function. And now I'll apply L'Hopital. So we get 2x over, and on the bottom, the derivative of 2 to the x is 2 to the x times ln 2. Of course, the derivative of 1 is 0, so that goes away. Now, as x approaches infinity, the top and the bottom, again, both approach infinity. So we can apply L'Hopital another time. One more time here. And then on top we get 2. On the bottom, the derivative of 2 to the x is 2 to the x ln 2. And we have another factor of ln 2 to bring down. So we have 2 to the x times ln 2 all squared. Now the top stays put at 2. The bottom is still blowing up. So this is 0. And that means that the limit that we were after, the limit as n approaches infinity, of n squared over 2 to the n plus 1 is equal to 0. So that converges. So another bit of notation that we're going to see is the factorial. You may have seen this in other instances, but the factorial is defined as follows. First of all, and I guess maybe I kind of put these in reverse order, but we define 0 factorial to be 1. N factorial is just the product from 1 up to n. And then it looks like 0 factorial kind of deviates from that, right? You would think, well, isn't 0 factorial equal to 0? The way I've written this definition, this sort of just tells me how I think of the factorial, right? Just multiply all the values. The factorial is really defined recursively. The recursive definition, first of all, we have an initial value, so we begin with 0 factorial is equal to 1. We just define that. And then we find n factorial is equal to n times n minus 1 factorial. So you can find n factorial by knowing the previous factorial. In that way, 0 factorial equals 1 is not inconsistent with the definition. But in how I actually think about and use it and use this value and compute it, that's the one that I've included here in the notes. Is what I think of as the most, is a useful way to define it. But it is also important to note that n factorial is n times n minus 1 factorial. It kind of contains the lower factorial as factors. Next, another result is the Squeeze theorem. So let's suppose I have two sequences, my ANs and BNs, and both of the ANs and BNs are approaching the same value, right? That's what that highlighted piece means. And suppose further that I have a sequence of CNs, and what I can say about the CNs is that for each term for term, the CN is always in between the corresponding AN and BN, meaning like C1 is between A1 and B1, C5 is between A5 and B5, C6 is between A6 and B6. Term for term, that's always true. If that's true, and both the ANs and the BNs approach L, then the only possibility for that CN is to also approach L. We call it the Squeeze theorem for a reason. Like that sequence of CNs is being squeezed to the same limit as the ANs and BNs. Here's a really kind of simple example of applying that. Suppose we have this sequence, Cn, which is defined by -1 to the n times 1 over n factorial. Now, usually when you apply the Squeeze theorem, you're given a sequence, and that's what you want to find out about, and it's up to you to come up with those two other sequences. So here there's kind of, I guess, maybe an obvious choice. We're going to let A sub n be the sequence whose terms are -1 over n factorial, and B sub n will be the sequence whose terms are +1 over n factorial. We'll observe that the limit as n approaches infinity of negative 1 over n factorial is 0. You know, n factorial, you know, is defined, right, as up here, the product of all the integers from 1 up to n. As n gets big, that product just gets huge. That product grows faster than just about any other function that you've ever looked at so far, right? It grows faster than exponential functions, in fact. So that n factorial is huge, which means 1 over n factorial is approaching 0. Similarly, or that's the negative 1 over n factorial. Similarly, the limit as n approaches infinity of positive 1 over n factorial is 0. And since negative 1 over n factorial is less than or equal to negative 1 to the n times 1 over n factorial, you know, this sequence in the middle, that just oscillates in between the two, which is less than or equal to positive 1 over n factorial. And that's true for all n. Here's what might be a new symbol. That little upside down A means for all. That means we can conclude that the limit as n approaches infinity of negative 1 to the n times 1 over n factorial is 0. Basically, we're saying we know this goes to 0. We know this goes to 0. And this sequence in the middle is being squeezed on either side and must also approach 0. The squeeze theorem only works when these two other sequences approach the same value. Next, we have the absolute value theorem. For if you have a sequence and the limit of the absolute values of the terms in the sequence approach 0, then the sequence itself has to approach 0. There's no other option, right? That's only true for 0, right? So if we say that the absolute values approach 1, that does not mean that the limit of the terms themselves approach anything. That could oscillate between negative 1 and 1, right? That you could have a variety of different behaviors. So this is only true if the absolute values approach 0. All right, so the next thing we're going to do is just talk a little bit about n factorial and 2 to the n. And then we'll actually extend that to any exponential, k to the n. So 4 to the n, 5 to the n, whatever. We're going to look specifically at n factorial and 2 to the n, but what we deduce will be true for any exponential function as well. So we're going to show why the limit as n approaches infinity of k to the n over n factorial is 0, no matter what k is. So we're going to show it first for 2 to the n. So first, let's observe that we can write the following. n factorial, remember the factorial is just the product of the integers from 1 up to n. So I'm going to write out the first several factors, times 2, times 3, times 4, times 5, times 6, right, and then all the way up to times n. And I'm going to group this. First, I'm going to just group these first 4 factors. 1 times 2 times 3 times 4, that's 24. And then we have times 5 times, then we have the rest of the factors. And right here, from 5 up to n, that's n minus 4 factors. And we can rewrite the expression n factorial in this way as long as, n is at least 4. And let's compare that with 2 to the n. So I've got n factors of 2. So 2 times 2 times 2 times 2, right? All the way up to times 2. I've got a total of n factors, and I'm going to do the same thing I did up here. I'm going to group the first 4 of these factors together. So 2 times 2 times 2 times 2 is 16. And then I have the rest of these factors. And there are n minus 4 factors of 2 here. And again, I can rewrite 2 to the n in this way as long as n is greater than or equal to 4. So let's look at what this means. Let's compare these two, okay? This means that for n greater than or equal to 4, n factorial is greater than 2 to the n, right? As soon as I get to n equals 4, n factorial is 24, add 2 to the 4 is 16, right? So n factorial is bigger, and it remains bigger because, look, for 2 to the n, I'm just always adding a factor of 2 each time. For n factorial, I'm adding factors that get bigger and bigger and bigger. So starting at n equals 4, n factorial is not only bigger, but as you increase n, it's bigger by more and more, right? Like you're adding bigger factors. So as n approaches infinity, each factor added to n factorial increases without bound. While each factor added to 2 to the n remains constant. Remains constant, in this case, at 2. So, in effect, the denominator, which is n factorial, grows so much faster. Than the numerator.
Or, I guess, have you emailed your teacher and asked what she suggests? Did she respond to one?
So we can conclude that the limit as n approaches infinity of 2 to the n over n factorial is equal to 0. So, you know, for any other value of k, as long as k is greater than 1, we can make the same conclusion. We can make the same argument and conclusion comparing the values of n factorial and k to the n.
Well, let's pick a lesson to start with. So if your earliest missing assignment.
Now, if k is bigger, you know, if you're looking at an exponential like 4 to the n or, you know, 10 to the n or whatever, it might take a little longer for n factorial to catch up to those values initially. But it will catch up, and as soon as it does, once it catches up, it will grow so much faster. So Factorial growth outpaces exponential growth every time. And that means that the limit as n approaches infinity of k to the n over n factorial is equal to 0 for all k greater than 1. Okay. So I wanted to go through this whole thing because there's going to be times when we need to compare this growth. We've just done all of the hard work so that anytime we encounter a scenario where we need to compare how fast n factorial grows to exponential growth, we know that factorial growth outpaces exponential growth. That means it outpaces polynomial growth too, right? Exponential growth outpaces polynomial growth. Factorial growth outpaces exponential growth. So if the factorial grows faster than basically any other thing that we've ever, studied or looked at as far as functions go. So, all right, now we're going to do a little bit of a change in the type of exercise here. Here they say, let's find the nth term of the sequence. In some ways, these problems, these examples kind of bother me because what they don't say is what they don't say is we're establishing a pattern, find it and tell me what comes next or what the nth term is. Because without that, for all I know, the next term in the sequence could be all zeros. A sequence can do anything. So what we should just understand is when they ask you this kind of question, what they're saying is we're establishing a pattern. Find it and tell me what it is. So when these terms are fractions, and a lot of the time they are, I find it helpful to try to observe a pattern separately in the numerator versus the denominator. In this first one, you'll note that you could check me on this. The top values are powers of 2. And the denominators, these numbers in the bottom, they're all odds. And so if I'm going to try to write the nth term, the powers of 2 up top, it does begin with 2 to the first, 2 squared, 2 cubed. So that'll be 2 to the n. And these are all odds. And an odd is either written in the form of 2n plus 1 or 2n minus 1, and we just want to make sure that we pick the right one and make sure that it works for these values. So since the first denominator is 1, then let's see, I think I'm going to pick the 2n minus 1. It's always a good idea once you've done this to check a few terms to make sure that it works for everything, that we haven't missed something. But this is the nth term of the sequence, and then it says determine convergence or divergence. So let's see if we can't evaluate this limit. Now, as n approaches infinity, both the top and the bottom approach infinity. So this is an infinity over infinity. They're not both polynomials, so I don't just have that algebraic trick. So we're going to want to use L'Hopital. I'm going to rewrite this as the limit as x approaches infinity, so we have continuous functions. Up top, the limit of 2 to the x, the derivative of 2 to the x is 2 to the x times ln x, times ln 2. And on the bottom, that derivative is just 2. Now, as x approaches infinity, the top blows up, the bottom stays constant, so this whole limit is infinite, which means the sequence diverges. Let's try another one. The top one, if you want to have a go at this before I kind of tell you my observations, feel free to pause the video. Up top, we've got values that are all 1 less than a power of 3. On the bottom, these values are all factorials. So this is n factorial. Also notice that the signs alternate. And that means that there's a factor of either -1 to the n or -1 to the n plus 1. So let's write this out. Our terms are, now it begins negative, which means when we plug in for n equals 1, we should get -1 to the n should be -1. So I think we actually want -1 to the n, so that when n is 1, that gives us a negative, and that jives with that sign. Up top, 1 less than a power, that's 1 less than 3 to the first. And then here is 3 squared minus 1. So this will be 3 to the n minus 1. And then on the bottom is n factorial. That's 1 factorial is 1. 2 factorial is 2 times 1, or 2. 3 factorial is 3 times 2 times 1. So there's the nth term. And from what we showed on the last page, we know that the limit as n approaches infinity of -1 to the n is 3 to the n minus 1 over n factorial. The -1 to the n, that doesn't really affect the size, right? That just affects the sign. We know that factorial growth outpaces exponential growth. So, and it outpaces it by a lot. So this limit is 0, which means it converges. All right, another definition, we say that a sequence is monotonic if the terms are either non-decreasing or non-increasing. That means that as you move out in the sequence, the terms either just keep getting bigger in size, or they keep getting smaller, or at least they don't alternate, they don't fluctuate, they don't go up and down and up and down. So we're going to determine whether each of these is monotonic, and I usually start just by writing out a first few terms. The first sequence here, the nth term is 3 plus -1 to the n. So we already worked with this series in example 1, and I think again in another example, or the first example in this chapter in another example. So we know that this sequence, we already found the first few terms, is 2, 4, 2, 4, right? It just keeps alternating like that. So look, from 2 to 4, that's an increase, and then from 4 to 2, that's a decrease. This is not monotonic, right? It goes up and down. Let's look at another one. These bn's, 2n over 1 plus n. So let's find the first few terms. If n is 1, we get 2 over 2, which is 1. If n is 2, we get 4 over 3. If n is 3, we get 6 over 4, which is 3 halves. If n is 4, we get 8 over 5. If n is 5, we get 10 over 6, which is 5/3. All right, so from 1 to 4/3, that's definitely an increase. And from 4/3 to 3 halves, that's 1 1/3 compared to 1.5, that's an increase. From 1.5 to 1 3/5, that's an increase. From 1 3/5 to 1 2/3, that's also an increase. You can show this if you're having a hard time just mentally making that evaluation. Just do the subtraction and see if you get a positive or a negative. But it looks like this is monotonic increasing, or monotonic non-decreasing at least. That's our hunch. Now we have to show it. It's not enough to just look at what happens to the first few terms and then say that's what's happening forever. There are infinitely many terms in this sequence. So now we have to show it. So the way we're going to show it is we're going to compare the Bn term to the Bn+1 term, the arbitrary nth and n+1 term, and show that the n+1 term is always bigger. So our Bn term, this is 2n over 1 plus n. We want to show that this is always less than or equal to, and we're not sure yet, so I'm putting a big question mark, the n+1 term, which will look like this. Right, now if that's true for all n, then we will have done our job. Then we will have shown that it is monotonic non-decreasing. Alright, so I'm going to just simplify the right side here. The left side I'm going to leave as is. And that's n plus 2. Now what I'm going to do, I've got this inequality with fractions. I'm going to clear denominators. I'm going to multiply both sides by n plus 2 times n plus 1. Now notice, this is a sequence, and we start with n equals 1, right? That's our first term, and then we just keep going bigger as n goes to infinity, meaning n plus 1 and n plus 2 are positive. We are multiplying both sides by a positive. And so what that means is after, we do our canceling and stuff, what we're left with, we're going to retain the sense of that inequality. We're not going to flip it. So 2n times n plus 2, is this less than or equal to 2 times n plus 1, times n plus 1. So let's just expand these out. On the left side I got 2n squared plus 4n, and I want to know, is this less than or equal to, if you multiply all this out, you get 2n squared plus 4n plus 2. And now if you gather all of your terms, like subtract 2n squared, subtract 4n, right, we get 0 less than or equal to 2. That is, in fact, true. Right, so no more question mark on that inequality sign. And that means that this sequence defined by the terms 2n over 1 plus n is monotonic, non-decreasing.
What about when this is REL? Is that a good one?
So it's definitely more work to show that something is monotonic than not. If it's not monotonic, you just have to show at least one spot, right, where it violates that. We saw here we had an increase and then a decrease, and so that was enough. If it is monotonic, there's more work to do to actually show that. Let's look at one more. Our CNs are defined by the nth term equal to n squared over 2 to the n minus 1. So if n is 1, we get 1 over 1, which is 1. If n is 2, we get 4 on top, on the bottom. 2 squared minus 1 is 3. If n is 3, we get 9 over 2 cubed is 8 minus 1 is 7. Now right off, I think actually we're kind of ready to draw a conclusion here. From 1 to 4/3 is definitely an increase. Now, if we want to compare 9/7 to 4/3, and I just want to know, is 9/7 bigger than 4/3? Right, so what sign goes here? And to do that comparison, just get a common denominator. So I'm going to get a common denominator of 21. So 3 times 9 is 27 over 21. 4 times 7 is 28 over 21. 27 is obviously less than 28. So this is a decrease. And so we're done. There's not any more work to do except to say that the sequence is not monotonic. All right, one more last bit to do in this section. One more definition. We say a sequence is bounded if there is a positive real number such that the absolute values of the terms are always less than or equal to that number m. We call m an upper bound for the sequence. So is this sequence bounded? Well, we know that the sequence, all of these values of the sequence are at least as big as 1. You know, if n is 1, then that term is equal to 1, and as n increases, these values actually increase. We also know, and we can say, that these terms, as n gets bigger and bigger and bigger, all of these terms are strictly less than 2. You could say less than or equal to is all we need. You could actually go further and say they're strictly less than 2. And the way I know that for sure is that if I actually just take a look at just this fraction, 2n over n, well, 2n over n is equal to 2. So 2n over n is equal to 2, but if I take that same fraction and say, you know what, I'm going to make the denominator a little bit bigger by adding 1, then that has the overall effect of decreasing the value of the fraction. If you increase the denominator, the fraction is smaller. So I know that these values are bounded above by 2. And we can use this, as it turns out, 2 will be our upper bound. So this is true for all n. So we could say that this is bounded. We can say that the absolute values of these Bn terms is less than or equal to 2 for all n. We care about bounded and monotonic because of this theorem. If a sequence is bounded and monotonic, then it converges. Now, notice this doesn't tell us what it, how to determine what it converges to. Some limits are harder to evaluate, but just knowing that something converges is valuable. So, 1 over n, if we look at the first example here, these terms are just determined by 1 over n. Now, this is a pretty simple sequence, and you could just probably evaluate the limit anyway, but we'll note that it is bounded. That's true. And is it monotonic? Yeah, it's monotonic. 1 over n is decreasing. The top stays constant. The denominator, as n gets bigger, the denominator gets bigger, and so those fractions shrink. So that means that that this sequence converges. And of course, we could, if you look at it and work with it for a few seconds, you can evaluate the limit and determine that it converges to 0. So for this next one, this Bn is determined, the nth term is n squared over n plus 1. So is this bounded? Well, certainly I think we could say that it's bounded below by a half, but is it bounded above? As n gets bigger, is there a limit to how much these terms can grow? And there actually isn't. There is no upper bound. The top is polynomial growth, that's n squared, like a quadratic, and on the bottom is linear. So that top will outpace, the growth on top will outpace the growth on the bottom. So there is no upper bound. If it's not bounded, it's not going to converge. It does happen to be monotonic. Yeah, it's monotonic, it's increasing without bound. So, not bounded is enough for us to say that it does not converge, or that it diverges. Our last one is the sequence, whose terms are -1 to the n. Now this one is definitely bounded, right? All the terms are between -1 and 1. Is it monotonic? No. It alternates, so it's not monotonic. Now, it should be noted that if a sequence is bounded but not monotonic, that does not allow us to conclude that it diverges. We have to examine the sequence itself. So this sequence is bounded but not monotonic. This doesn't allow us to conclude that it is divergent. Doesn't allow us to conclude anything about the sequence. Now, if you look at the sequence, you know, the terms just bounce back and forth between 1 and -1. We could see pretty clearly this sequence diverges, right? There's no single value that it gets closer to. So this sequence does diverge, but it's not because of Theorem 15. Okay.